Morning students, today we are going to discuss about the various types of functions like one-one function or injection, on-to function or surjection, then one-one and on-to function or bijection, and solve some of the problems relating to the injective and surjective functions. And prior to this, we have already discussed about the relations as well as the functions. Means under what condition a relation becomes a function. Now coming to one-one function or one-to-one function, it is defined as each element of set A is mapped with a unique element of set B, or we can say each element of set A has a unique image on set B. Or in brief, let us consider f is a function whose domain is A. The function is said to be an injective function if for all x and y belonging to set A, whenever fx is equal to fy, x is equal to y, or we can say x is not equal to y implies fx is not equal to fy. That means a function will be one-one if distinct elements have distinct images, and this is the working rule for proving a function one-one. So now to prove a function one-one, we choose any two arbitrary elements x and y belonging to the domain. Assuming that their images, that is fx and fy, are equal, if we can prove that x is equal to y, then the function is one-one. Now some of the examples of one-one functions are the identity function defined from a non-empty set to a non-empty set is always injective in nature. The function f defined from R to R such that fx is equal to 2x is injective in nature. Similarly, the function f from R to R, fx is equal to 2x plus 1 is also injective in nature. And these things we will be proving it after some time. Now the number of one-one functions that are defined from a set A to a set B containing m and n elements respectively is given by npm when n is greater than or equal to m, and it is 0 when n is less than m. Now this set A has m number of elements, set B has n number of elements, and the number of one-one functions must be npm if n is greater than or equal to m, and it will be 0 if n is less than m. Geometrically, a function can also be, we can prove a function as one-one or not. And there is a test called horizontal line test, or we call it geometry test, for finding whether a function is one-one or not. If a horizontal line can intersect the graph of the function more than one time, then the function is not mapped as one-to-one. Here in this figure, we find that this is the curve, and we have drawn a horizontal line. That horizontal line intersects this graph at two distinct points. Here we find that x1 has image fx1 and x2 has the image fx2, and from the graph it's very clear that fx1 is equal to fx2, but x1 is not equal to x2, so the function is not one-one. Contrary to this, if the horizontal line intersects the graph exactly at one point, then we say the function is a one-one function. Taking one example, let us say set A contains 3 elements, 1, 2, 3, and set B contains 4 elements, A, B, C, D. That means this is the domain set, this is the codomain set. Now some of the relations are defined And we know a relation becomes a function if it is not one many. That means no element can have more than one image. So accordingly, this relation, it is not a function because one has the image B, again one has the image C. So this element 1 has more than one image. So element 1 has more than one image. So it is not a function. Now this is a function. 1 is associated to C and 2 is associated to C. But it is not a one-on function because two different elements have the same image. So it is not one-on. Here in this case, element 1 has the image A, 2 has the image B, 3 has the image C. That means three different elements have three different images. So we say this function is a one-on function. Now one example. Let f is a function defined from R to R such that f of a is equal to 3aq minus 4. Now we'll prove that this function is a one-on function. So for this, we choose any two arbitrary elements x and y belonging to R with the condition that fx is equal to fy. Thereby we get 3xq minus 4 is equal to 3yq minus 4, and cancelling minus 4 on both the sides, we find that 3xq is equal to 3yq and hence xq is equal to yq. And we know if the cubes of two real numbers are equal, then the real numbers must be equal. So we find that x is equal to y. So now assuming that fx is equal to fy, we prove that x is equal to y. So the function is one-on function. Next is your onto function or surjection or surjective function. A function is surjective if each possible image is mapped to by at least one argument. In other words, each element in the codomain has non-empty pre-image. Or you can say a function is surjective if its range is equal to its codomain. So here in this diagram we find that this element 1 has at least one pre-image. Element 2 has exactly one pre-image. Element 3 has exactly one pre-image. So here we find that codomain contains the elements 1, 2, 3 and a range also contains the elements 1, 2, 3. So codomain is the same as range. So the function is onto. Contrary to this, in the second figure we find that there is an element 4 in the codomain which does not have any pre-image. That means here codomain contains the elements 1, 2, 3 and 4, whereas the range, which is the collection of all the images, is containing the elements 1, 2 and 3. That means codomain is not the same as range. So this function is not onto. Now let us take one example. Set A contains elements 1, 5, 8 and 9. Set B contains the elements 2 and 4. Now we have defined the function f containing 4 order pairs 1, 2, 5, 4, 8, 2 and 9, 4. Now we have to prove that this function is onto. Now f is the function 1, 2, 5, 4, 8, 2 and 9, 4. So here this element 2 has the pre-image 1. Again this element 2 has pre-image 8. That means the same element 2 of the codomain has at least one pre-image. Similarly, the element 4 in the codomain has at least one pre-image 9 and 5. That means here the range of this function is 2, 4. The set containing 2 and 4. Whereas the codomain is also the set containing 2, 4. That means codomain is equal to range. So the function is onto. Now the number of onto functions that can be defined from a set containing n number of elements to a set B containing m number of elements is given by m to the power n minus m plus m into m minus 1 to the power n minus m minus 1. If n is less than m, the number of onto functions becomes 0. And if n is equal to m, that means the number of elements in A and B are equal, then the number of onto functions that can be defined from A to B is factorial m. Next is your bijective function, or you can call it 1, 1 and onto function. Now a function f from A to B is said to be an onto function if it is both 1, 1 and onto. That means distinct elements of the domain have distinct images in the codomain, and in order to be onto, no element in the codomain will be left out. That means codomain must be equal to range, and accordingly we can say a function f from A to B is both 1 to 1 and onto when no element of B is the image of more than one element in A, and all elements in B are used. Functions that are both 1 to 1 and onto are called bijective functions. Now an example of a bijective function. We have a function f defined from R to R such that fx is equal to 3x minus 5. Now we'll prove that it is a bijection. That means first of all we have to prove that it is 1, 1. Then we'll prove that it is onto. Now to prove it 1, 1, we consider any two arbitrary elements belonging to the domain. Let us say x and y are any two arbitrary elements belonging to the domain R, such that fx is equal to fy. Thereby we get 3x minus 5 is equal to 3y minus 5. So cancelling minus 5 from both sides, we get 3x is equal to 3y, and hence x is equal to y. So assuming that f of x is equal to f of y, we prove that x is equal to y. So the function is 1, 1. Now to prove the function onto, we choose any arbitrary element y belonging to the codomain, and that y is equal to fx is equal to 3x minus 5. And now we express x in terms of y, and so we get x is equal to y plus 5 by 3. Now what is y? Y is a real number. Y plus 5 is also a real number. So a real number by 3 is also a real number. That means x belongs to R. That means we find whenever any y belongs to R, its pre-image also belongs to R. That means x belongs to R. Now that x being associated to f produces y, because fx is equal to f of, in place of x we substitute y plus 5 by 3, and on simplification it becomes 3 into y plus 5 by 3 minus 5, which is equal to y. So the function is onto. And in the same way, we can find that this function, when defined from natural number to natural number, will be 1, 1, but it will not be an onto function, because when x belongs to set of natural numbers, x plus 5 is a natural number, but x plus 5 by 3 is not necessarily a natural number. That means we cannot prove the existence of x, and hence the function is not onto. Thereby we can say that it is not a bijective function or bijection. Now please try to explain the following. Explain why the following are true. The identity function is always injective. The function f from R to R such that fx is equal to 2x is always injective. So some of the functions are given. So please answer why these things are true. So thank you, students. Control C.